Okay, Paul, Wouter, Piotr, floor to you.
Wonderful. Thank you very much indeed, Marco. And since we have you with us, huge congratulations on setting up Remtech Europe and making it such a huge success. And I think the global reach is amazing. And we're going to benefit from that this afternoon as we are joined by colleagues from Brazil as well. My name is Paul Nathaniel. I'm going to be chairing the session with two colleagues of mine who will introduce themselves in a minute, Peter and Walter. So welcome to session 6 of Remtech Europe on LNAPL and chlorinated compound remediation. I hope you've enjoyed the previous sessions. If you've missed any, they're all recorded and available online. And that you realize you've got 3 more days of this event to go for. And a little plug for what I'm doing on Friday afternoon, which is a training session on PFAS in shallow groundwater. But the way we're going to run this afternoon is we have a number of presenters. Peter and Walter will introduce themselves and then the speakers. And then at the end, we will have a panel discussion where we will make sure that every speaker gets asked at least one question. It would be better if that question came from you, the audience, rather than from us, the chairs, but we have some up our sleeve if we need to. So without further ado, I'm going to ask Walter first to introduce himself, and then Peter, you can introduce our first speaker, if that's okay.
Good afternoon as well from my side. My name is Wouter Gevaerts. I am working and living in Belgium. I'm as well, I put a lot of energy in NICOL. NICOL is a network for contaminated land in Europe, and I'm leading the service provider group at this moment. And I have to be paid as well, and therefore Arcadis is willing to pay me for the job I do for Arcadis. I'm an environmental director within Arcadis Europe, focusing on environment and even focusing a bit more on contaminated lands.
Thank you, Walter. Piotr?
Hello, everybody. I'm Piotr Wojda. I work for the European Commission for the Joint Research Center. And my center of interest is soil and pollution coming from different sources. So looking how to prevent pollution and then how to solve problems that might eventually arise. I'm also trying to combine agricultural data for soil health issues. I'm very glad that I can participate in the Remtech Europe. It's really already exciting exercise, and I'm looking forward to the presentations, especially of today's session. Maybe I will leave the floor to the speakers, and let me introduce the first presentation we are going to listen to. It's in situ treatment of BTEX and CVOC under a large car manufacturing industrial plant that will be presented by Marcello Carboni and prepared together with Gareth Leonard and Chris Merten. So let's listen to this Belgian story concerning this industrial site. The floor is yours, Marcello.
Okay, thank you very much, Piotr. Can you all listen to me? And I hope you can also see my screen properly. Okay, yes. So good evening, everybody. I'm presenting over a case study of different in situ treatment technologies that have been integrated between them for treating an active car manufacturing plant. We are talking, in fact, about the Volvo car plant in Ghent, Belgium. This is, in fact, the first plant that Volvo installed outside Sweden in Europe. Just to give you some numbers, there are more than 5,000 workers employed there, which are producing around 250,000 cars per year. Production activities are quite typical of this kind of manufacturing, so include welding, painting, final assembly, and those activities make use of lubricating oils, cleaning solvents, and as you can imagine, through the years, this plant dates 1965, there have been several leakages or spills, which then cause soil and groundwater contamination. We are talking about a very typical geological setting for Belgium. So fine, homogeneous sand, very superficial aquifer conditions. The company Artemis Milieu has done the investigation at this site. They have detected several small sources, but between them, two areas have more formed contamination. So we are calling them area 1, which contamination is related to the paint mix plant. This suffers from, let's say, mid to low range of contamination, and it's BTEX and TPH there in groundwater. Another area is more down gradient. Here, there has not been found any direct correlation with an existing plant. It stands below the wastewater treatment plant, actually. But here, the concentration are much, much higher. So it's about 10, 20,000 micrograms per liter. And we've also commingled contamination. So BTEX are standing together with chlorinated solvents. Mainly it's TCA, but there are also some DCA and some traces also of vinyl chloride. So here we can see a map showing the two contaminated areas. And as you can see, today the contamination is not arriving to the site property boundaries, but cutting down the risk for off-site migration. This is the primary goal and driver for the remediation in this case. Due to the different concentration especially, the strategy for remediation has been different for the two areas. So PLUME 1 has got low concentration of residual contamination. So this went with a strategy with an injection barrier down gradient of the contaminated area. Instead, the area 2, which suffers from much higher concentration, this went for a grid of treatment, grid of injection on the wall contaminated area. But now we will go more into the details of the two areas. So starting from area 1, I recall this is just TPH and BTEX contamination. So the decision was for injecting a barrier which would cover the down gradient side, and this has a length of 60 meters. This has been divided into 3 portions. So the middle portion has been used for the pilot test. The 2 lateral wings then have been injected in the full scale. The main goal here was to try to achieve the complete remediation just with one single injection. We are talking about a very intensive manufacturing plant. So one of the main scope for defining the strategy was, let's try to minimize any disruption and interference with ongoing activities. So the strategy selected was with enhancement of aerobic biodegradation through in situ sorption, using a technology which is named PLUME STOP. This is a colloidal activated carbon. So we mill it down to 1 or 2 microns. This is a couple of orders of magnitude less than powder activated carbon. We coat it superficially with dispersive agent. This makes it behave like an ink. So it can be injected smoothly at low pressure, and it distributes widely and homogeneously into the subsurface. So what it does, it what it does, it coats the soil surface, And then being a carbon, of course, it sorbs the contaminant. But what is important is that the sorbed contaminant, in this case, TPH and VTEX, remain perfectly bioavailable. So this carbon gets colonized by the biodegrading bacteria, and these cause destruction of the mass of contamination. So biodegradation provides a complete regeneration of the activated carbon. This makes that even if we are designing a barrier, like in this case, and even if contamination continues to drive through our treatment barrier, the colloidal activated carbon will always be available over time to deal with this contamination. Here is the pilot, so a 6 injection point, and we did monitor both from wells which are inside the treatment barrier, so not the same injection well, but external from the injection well, but inside the treatment barrier, and wells which are down gradient of the barrier. This has been done with a fixed injection well, and the injection have been performed using Parkers. And here are the results. So, of course, this graph is very stunning, is very good, but it's quite typical of what we usually observe with PLUME STOP. So it's very quick as a technology, and this is mainly due to sorption effect, which is fast. And also tends to be quite stable over time, so doesn't suffer from fluctuation or from rebound effect over the long term. We were starting from majority of wells 1 or 2 milligrams per liter. Just one single well was higher concentration. Thanks to this, then we have been able to design the full scale. What is important to notice is that in the full scale, the pilot area has not been reinjected. This is because the process, if the design is accurate, if the injection went well, then there is no need for reapplying over time. We just slightly changed the dose because of different baseline conditions on the 2 wings compared to the central part of the plume. And results for full scale, I will show you first the, this is the average of all the wells that are down gradient of the pilot side. This is because this can show a longer time frame for the data. So we are 3 years now. And as you can see, the decrease in concentration continues and is maintaining a very stable over time. The average wells instead of on the 2 lateral wings show a similar behavior, but we have of course a shorter data sets. Then let's go to see what happened instead in area 2. This, just to give you some background, initially the strategy in area 2 was supposed to be very similar to what we did in area 1, so a PLUME STOP barrier. Then there was some additional site investigation. We discovered that there was a really high concentration, and this was expected as excessive mass for PLUME STOP technology, because PLUME STOP works at its best in the mid to low range of concentration. So we decided as a strategy to go with a preliminary phase with ISCO. This was meant to deal with removing with oxidation the majority of the mass, and then to deal just with a phase 2 with colloidal activated carbon. So as ISCO agent, Regenox has been selected. This is because it's the only oxidizer that is non-corrosive. So unlike permanganate and persulfate, for example, which can cause corrosion of metals material, Regenox is completely compatible. So here we had some services which needed to be preserved. So this is the reason for the selection. The PLUME stop this time has been applied not with oxygen release compound, as we did in area 1 for biostimulating TPH and BTEX. Here we decided to co-apply with hydrogen release compound. This is because we wanted to biostimulate anaerobic biodegradation, because in this area the main driver of the risk are the chlorinated etanes, not the BTEX. And we also applied some microbes, an inoculum of microbes for biomediation. The strategy was different because we applied a regular grid. So the red dots are the ISCO injection point. This, in fact, is just where the concentration are much higher, so not the entire area 2. There was not complete access to the wall area because on the surface there is the wastewater treatment plant. But even with that, the results were quite satisfying. And then for phase 2, there was another regular grid of injection on the wall area for PLUME stop HRC and BDI. The injection went direct push using a particularly small rig. This is because we needed to avoid as much as we could interference with ongoing manufacturing activities. Also, we used very low pressure. We are talking about permeable layers. We went even below 1 bar or keeping between 1 and 2 bar as a maximum. This is because we want to achieve as much as we can a homogeneous distribution, and this can't be reached with high pressure injection and fracturing. About results of area 2, as you can see, we started from much higher concentrations, so 10, 20,000 micrograms per liter as a baseline, both for BTEX and chlorinated. You may argue that the ISCO phase has increased the concentration, and then we are getting back just to concentration which are the same order of magnitude as we started. But ISCO, and in particular Regenox, which is based on percarbonate, tend to be also with a desorbing effect. This makes that a lot of mass from the saturated soil is moved into the aquifer, where then it is oxidized. So even if we are getting back to the same dissolved phase concentration, the total mass of contaminants that has been oxidized was is expected to be quite high. So these, even if we are then starting with a baseline for the colloidal activity carbon quite high, and this would be probably too high concentration for PLUME stop to manage, but because the mass was made poor by the ISCO phase initially, this was considered in any case applicable. So after the colloidal activity carbon with hydrogen release compound application, as you can see, the behavior is pretty similar to what we observed in area 1. So what can we conclude? I would say, and I like to stress on this, that not just the pilot, but also the additional site investigation in this case have been crucial to be able to optimize the injection approach, redesign and revise the application for full scale, and to be as much as we could accurate and cost effective. Most of the time, pilot and investigation are perceived as extra cost, but these can save, in many cases, like this one, a lot of time and cost. Just to give you an idea, the total cost of the application for both areas was below 350,000 euros, including everything of the groundwater remediation. All these has been achieved getting as minimum as we could interference and disruption with the manufacturing plant. This is because we don't need any ongoing maintenance of any plant. And thanks to PLUME STOP, we don't need repeated injection over time. So we just go once, we apply, and then all we need to do is monitor on the long term. Still, the monitoring is ongoing for this site. The monitoring frequency has been decreased, but this will allow us over time to see how effectively it performs over the years. Thanks to this strategy, then, the client has been very happy to be able to get quite quick removal of their off-site liability, and at the same time being able to maintain this over the long term. Okay, with that, I finished. I thank you very much for your attention.
Thank you very much, Marcello, for your very interesting presentation. And I think that the questions will come later on. And now I will maybe pass the floor to Wouter to clutch into the next session.
Piotr, you can go on. That makes life easier. A uniform.
Okay, well, I'm going to jump in and introduce, otherwise we're going to run out of time.
Yeah.
So I'm delighted to cross the pond to North America, to George Ivey, and invite him to present his paper on surfactant enhanced extraction at LNAPL and DNAPL impacted sites, pilot to full-scale applications in Canada, the United States, and Europe. And George, let us know where you are on the planet as you address us. Thank you. Don't forget to unmute yourself, George.
Okay, I think I've been unmuted now, so I'm going to see if I can get my presentation up and going. Just bear with me. There we go. So yeah, I'm actually presenting to you from Vancouver, Canada. It's a little early in the morning for me, so I'm enjoying a nice cup of coffee. I've only got 15 minutes, so today I'm going to really stress a little more about explaining how the technology works, and decided to just settle on just doing one super fun site application in New York City to convey how the technology works. I'd like to thank Marco for helping out with this session number 6. The RemTech organizers, particularly Sylvia Parpella, I hope I got her name right, my fellow speakers, and as you can see, we're represented in Italy by BAW. So without further ado, let me get going on. For those individuals that are interested in a copy of my PowerPoint, please, I said this will be recorded, but if someone like a PDF, feel free to reach out to me, as I'd be happy to email that, and I'll provide my contact information at the end. So
George, can I just jump in a second? Can anybody see George's screen? Because I can't. Can you press the green share screen button, George?
Okay, let me see. Can you see me now?
Not yet. Yes, it's waking up.
Okay, so yeah,
just a while to get to us from Vancouver. The floor is yours.
Okay, so let me get this wide open again. Okay, so getting on, the next thing I want to bring to everyone's attention is my actually background as a synthetic organic chemist that did geological engineering, later got a master's in project management. So developing products which are safe and pure are very important to us. So our PFOA, PFOS-free, 1,4-dioxane-free, dioxin-furanes, PCBs have been tested and they're free of every US EPA regulated compound. Some people say there's a claim no one else is making, but we've always been very, very keen on purity since I started the company in the early 1990s. So and we're also REACH compliant. So moving on, when we're dealing with LNAPLs, they go by a number of different names depending upon where you are in the world and who's dealing with them. NAPLs, LNAPLs, DNAPLs, phase separated hydrocarbons, or just simply free product. This is a function of the behavior of these contaminants in the simplest sense from a chemistry perspective. The lighter things are tend to have a lighter density than water, so they tend to float. And the things that are typically chlorinated, fluorinated, or brominated tend to sink. And we tend to have that understanding on how they behave. But this overlooks something that's really important. When you're dealing with the contact between a vapor and water, or a petroleum product, or a chlorinated solvent, or those amongst themselves, what really affects their movement in these small pore spaces, interstitial spaces within the subsurface, is actually governed by interfacial tension. And overlooking that, unfortunately, will make us overlook a really important factor in its behavior. So often when I'm looking at contaminants, just like a doctor looking at a patient, the better you understand the site, as our previous presenter said, doing a pilot, doing some extra investigation, getting that data as to why they come into our office, presenting these symptoms of not being well, so that we can better diagnose them and then apply a remedy that's much more effective. And again, on typical sites where we have spills, we know things move along the surface. They can penetrate, causing vapor phase impacts, soil, groundwater, and depending upon the density, these will also affect their movement. And some organic contaminants have a degree of solubility, even though it's not great, and then move as a plume. What I'm showing here is actually a baler from a site that we're involved with near Melbourne, Australia. And what you actually have here are multiple phases. We have LNAPL at the top, DNAPL, and we have some intermediate phase compounds. So our tendency to think that things either float or they sink is actually not true. There's a lot of different phases and they have a tendency of behaving differently. If you've ever gone to a bar and had a bartender make you a drink with 4 different layers or 3 different layers of fluids, they're actually taking advantage of this very fact. It even happens with our contaminants. So what I'm showing here is that when we're dealing with contaminants such as vapor, because there is vapor intrusion, we have soil impacts, groundwater, not only with those vapors getting trapped in there, we have contaminants getting trapped, and water sometimes become immobile. If we can't get into those interfacial spaces, those pathways that are in there, this is where contaminants are trapped. And depending on whether we're delivering something that things absorb to, some physical, chemical, or biological method, we have to understand their behavior. And in doing so, it creates an opportunity for us. And not only do we have LNAPL, we have droplets of these NAPL compounds that can get trapped in there. And they're trapped again by the interfacial tension because they really can't move past the water that has them trapped, or maybe it's a gas bubble or what have you. And this really does affect why contaminants reside and linger at times. So interfacial tension becomes very, very important when you're looking at things like most contaminants are in the low 20s, whereas compared to water, it's around 73 dynes. So it almost acts like a cork on a bottle. So it makes it difficult for them to get through. But there are ways of breaking the rules of chemistry and improving access and getting those out, or regress of those contaminants from those systems. So there are options for vapors, NAPL, so on and so forth. When we're dealing with contaminants, just like reactions, access to contaminants is really important for reaction kinetics, something that's been getting in discussions and texts and whatnot for 500 to 1,000 years. So I'm showing here on the left side are adsorbed contaminants. The typical behavior of a lot of organics, which are not strongly soluble, they tend to phase partition and stick on surfaces. And when they're adsorbed, they're generally less available to physical, chemical, and biological activities. So what I try to do with the IV-Sol surfactants is take things which are generally immiscible and make them, shall we say, soluble or stabilized in solution, so they're now more available. We've even done things with people that are injecting things such as BOSS or PLUME STOP to get those, such as free product or other things off, to actually allow them to have even faster access and also allow for the injection to spread greater. So I'm a big fan of merging and combining technologies as it works, as the previous presentation spoke about combining technology. So when you're having things that are adsorbed, they're less physically available for MPE, pump and treatment, soil washing. You have biological processes, anaerobic, aerobic, facultative, those processes can be hindered. And the chemical availability of contaminants, oxidative, reductive, and there's other reactions that we don't spend a lot of time on in our industry that we should. So the way IV-Sol works is most contaminants, again, will tend to phase partition onto surfaces. Then at a molecular level, IV-Sol interacts with those. So as an organic chemist, my thought was, if I take Marco, for example, and we say Marco's an oil droplet, and we want to make Marco miscible, the way about 99% of surfactants work is, if a surfactant's a ping pong ball, I cover Marco with 500 ping pong balls, and I make them float like a spaceman in that pore space. where he's apparently, hopefully more available. Unfortunately, being covered by 500 ping pong balls does inhibit his physical, chemical, biological availability. So I understood that molecules have an ear, a nose, an arm, a hand, a foot, various regions on their molecules. So if I have an affinity for those regions, I don't need to cover him with 500 ping pong balls to make him more available or working below the critical micelle concentration. So this is what I perfected, and I've been applying around the world with great success on making contaminants more available physically, chemically, biologically. This image here is showing what happens when you cover a Marco with 500 ping pong balls and he's stuck in the center. This is not what you want to do. The other thing is, in that situation, he's emulsified. Good luck running him through an oil water separator or any other type of normal water treatment system to achieve your discharge limits. You're going to be challenged. It's very difficult to do. In our case, you can use oil water separators and all the standard water treatment systems. This I'm going to show is an oil droplet, a water droplet on water. And the reason I show it is just to beg the question, how can that water sit on this fine sand? That seems kind of odd. Well, the reason is I want you to understand what water really is. And I hate to tell you, water's not H2O. So not only is IBCell looking at making things that don't want to dissolve, but it can also change the behavior of water. Okay, this should get interesting, shouldn't it? Let's go on. We all know from school that everything on the periodic table in the upper right-hand corner, oxygen, sulfur, chlorine, fluorine, those things are more electronegative. Things way up over there on the left, like sodium, calcium, hydrogen, are electropositive. So we just put these delta symbols on them. And it kind of explains their behavior. They behave much like magnets. So we have been told in grade school, or maybe in your introductory courses in chemistry and university, that the oxygen on one molecule will be attracted to the hydrogen on the other, doing something called hydrogen bonding. And that's usually where they stop on this explanation, but there's more to it. So I'm going to explain to you what it really is. So expanding upon that, the water molecule is attracted to its neighbor, but then that one's attracted to its neighbor, and it does so three-dimensionally. So what ends up happening, some people refer to water as a liquid crystal, it forms a water cluster. This explains why this water cluster is somewhat impeded or retarded in its movement through finer grain geology, or your K value starts to drop. If you could reduce the size of that water cluster so it's smaller, oh, now we can get access and regress within finer grain geology. Or even a sandy site, you have three of them, one's more compacted than the other. Well, that more compacted site actually has reduced K. Well, this would allow us to actually do that. So not only can we overcome solubility issues, we can now change the behavior of water to allow for better access and regress during treatment. A nice illustration is, imagine we've got water and we're trying to get into this trapped contamination or globules in some geology that just won't go out. Well, by changing the size of the water clusters and carrying those IBCell molecules into that area of concern, we can then act on that and get that stuff miscible where it can be physically pulled out or made more available to bacteria. Or in other cases, maybe you're working with oxidizing or reducing agents or something akin to that. So that by having these more available, it creates opportunity positions for you. You can use this on our own or combine this with technologies. I find that all very exciting, and it's great to do. At the end of the day, we want success for our clients. I'm going to show one three-dimensional animation of a typical application that we do. This would be an in-situ application. Like many sites, we go in, we investigate it, looking for vapor intrusion, soil, maybe sediments in some cases, groundwater contamination. Based upon that investigation, you can place vertical, angled, or horizontal wells such that whatever we're introducing for the IBCell, we can make contact. In this scenario, we're showing some 100 millimeter wells. We can gravity feed or use a little bit of pressure, and we can actually cause some mounding around the well or place a packer to better contact during the smear zone, allow it to inject, wait a period of time called the residence time before you complete the extraction. Mostly on average, that's about 24 hours. What I'm simulating here by this each event is a sequential extraction. This has been written up for hundreds of years and is done by every organic chemist in the world when we're extracting products from samples. When the lab gets your samples into the lab, they're doing a sequential extraction to get your stuff out to quantify it. So essentially when I put the surfactants in, my IBCell ones, I'm putting it in, they're making contact, they're making contaminants available, and I can remove that mass in the event. Repeat it, remove some mass, repeat it. Quite often, I get involved with sites where we have a lot of LNAPL contamination, which stoichiometrically makes a lot of treatment applications, which could be BOS, which could be chemical oxidation, which could be biological, and reduce that, stop, and then they continue on with those suites of technologies with great success. And we've got lots of case studies like that. It's a lot of fun. So I'm going to talk about one Superfund site that we got involved with because I'm limited on time. This one's in New York City, so we're all aware of where that location is. And it's the Sunnyside Yard. If you were to look kind of northeast from here, you can see the Empire State Building in Manhattan. So we had a pretty interesting view while we were working there. It's about a 130-acre site. I can't remember what that is in hectares. I apologize, but I'm using American references because it's an American site. It was in operation for over 100 years. It's a state Superfund site. There's actually about 6 operational units or contaminated areas on this. And the one we were working on is where the star is shown, where they're running a multi-phase extraction system to try to deal with a lot of free-phase contamination and get that mass removed. And then they contacted, we did some bench scale work, just like you heard in the previous thing, which helped the client refine our application for field trials. This just talks about some of their terms of reference. We learned during our bench scale studies that they had some PCBs in the soils, and they were quite concerned that we wouldn't mobilize those during the IV soil application because the PCB limits in soils were acceptable, but if we mobilized in the groundwater, the limits were much, much lower. We showed that we could recover the hydrocarbons by 4 to 5 orders of magnitude over the hydrocarbons over the PCB, sorry, which was very, very favorable, and that held true even at field scale. So they really wanted to get rid of the free product here is the biggest risk. This shows a network of their multi-phase extraction wells in the site, and some of them actually had lines leading under rail lines to remote locations. Or an air photo of this shows the same thing. That kind of vertical building you see in the bottom center is actually their treatment system, a bunch of lines going out to a lot of the multi-phase extraction wells. And if you ever run a multi-phase extraction type thing or dual phase vapor extraction, they go by different names, you will actually find that the vast majority of the contaminant mass you recover happens early on in its life cycle. Or in this case, 84% of the mass that recovered happened in the first 5 months. So this system ran from 2013 please mute yourself, please. From the 2013 to 2015. And obviously it was plateauing and they were reducing the amount of mass they were recovering. So just bringing that forward. So they picked 8 of the more challenging wells in which they have LNAPL presenting itself to see if we could help enhance the multi-phase extraction system for recovery. They had great communication hydrogeologically with the site. They just could not deal with this phase that was these globules and the floating phase, as well as some very significant absorb phase. So our goal was to introduce our product, overcome that, increase availability for recovery. We did all of our applications through gravity feed. They typically were injecting at one well and pulling from the same well. In some cases, they injected at one well and they swept it subsurfacely to an extraction well. We also have a field surfactant test kit that we developed, which you see in the foreground showing no surfactant traces in increasing amounts. So it allows you to actually see what's going on in situ. It's very, very helpful. Clients like it, very inexpensive as well. This actually shows the free product percent removal that they achieved at those 8 locations. And the average inside 1 week was 81%. I'm happy to say after we did the pilot, we went to full scale, and literally it was 3 to 4 months we were concluding the application at this site. It's completely redeveloped. So in conclusion, the LNAPL recovery enhanced the LNAPL recovery for the site. They were very pleased with that, getting it out. They were really happy that from application to extraction, it could be done very quickly within 24 hours. They tried higher concentrations, like 1 to 20, 125, and they realized it only has 1 hand. Well, putting in something to grab 6 hands is not going to do any better, so you're better off only to apply it at the appropriate concentration. And again, it was very, very effective. They also started to use us on other operational units on the Superfund site, which was nice. Really quickly in concluding, I'm happy to share in the United States, we won the top 10 Environmental Technology Solution Awards this year, which is great. And in Europe, for those that are interested, we have regional representation by BAW, Terra Correct out of Belgium, BAW's out of Italy, and Lion over there in Poland. And this is our contact information. So I thank you for your time, and feel free to approach me during the panel session with Q&A.
Thanks very much indeed, George. I'm going to hand over to Piotr now. And I think you said you would be willing to make your slides available if anybody got in touch with you. Is that right, George?
That is correct.
Wonderful. Piotr, over to you.
Okay, thank you very much. So yeah, let's go to the next presentation, which title is Expedited and DNAPL Destruction Bio biostimulation presented by Kent. So let's hear about the former electronic manufacturer in Ohio. So please, Kent, the floor is yours.
Hello, everyone. Afternoon, morning, whatever it may be. Thank you very much. Bud, great seeing you. My background, I'm president of TerraStrike. Let me get full, I'm sorry, guys.
Kent, thank you. I was
Yep,
about to
here we go.
ask you to go in.
There we go. Hang on, let me get up. Oh, geez, hang on. Don't get dizzy. We'll be there in a second. I'm president of TerraStrike. I'm out of New England in New Hampshire, the United States. Manufacturer, my partner is out of Canada, up in Brampton, Ontario. I've been in the industry for about 40 years. Jack of all trades, classically a master of none. This is my first visit to Italy, and I want to thank you all. You've made me feel just like I'm at home. And it is through a collaboration with a very, very close friend of mine, Richard Schaffner, who I worked with together at GZA for 7 years and then collaborated 10 years hence, who should be giving this presentation, but unfortunately, about 12, 15 months ago, Richard suffered a massive stroke and is no longer with us. But it's to him I owe where I am today and what TerraStrike is today. What is biostimulation? What we do is we try to enhance what Mother Nature has been doing since time began. It took about 100,000 years for the primordial soup to allow prokaryotes to develop. And we're trying to harness that activity by harnessing prokaryotic activity, looking at a treatment zone as an ecosystem, and amending that ecosystem with necessary nutrients, et cetera, to eliminate limiting factors to microbial development. And one of the things we really ask is that we stop looking at microbes individually as what the individual does, but rather look at, as I said, the treatment zone as an ecosystem. And let's look at what do microbes as a population need to develop. Many will argue that prokaryotes are a single species that just has incredible adaptive capabilities. It is through these adaptive capabilities that if we enhance that ecosystem, they'll do the work for us and create sustainable destruction of chlorinated solvents. And that's what we're going to talk about today. I love this slide just because it's kind of fun. What is not biostimulation? Gross excavation of contaminants, but I will never argue elimination of source zone wherever possible. And on our products and our strategies are completely amendable in a treatment train. And for an instance here at the end of an excavation, apply our additive to the bottom or the floor of that excavation to enhance long-term degradation of residual contaminants. We're going to talk about ERD Enhanced. It's our flagship product. It's a carbon-based additive combined with a saturated carbohydrate in our proprietary macro-micro inorganic nutrient formulation. And like I said, it eliminates the limiting factors to subsurface ecosystem and maximizes enhanced reductive dechlorination organically. We enhance the indigenous populations. We do not augment. We do not introduce laboratory bugs to the subsurface, but you can. Our additive will just make them more effective, but we find that laboratory-induced bugs are basically outcompeted by the natives. And we're looking into research at this time that augmentation, the introduction of bugs, is actually gene therapy. And I can talk about that in a little bit. We promote sustainable degradation of organic contaminants to include chlorinated volatile organics, halogenated aromatics. And we do believe, what I will talk about towards the end of this process, the development of biofilm, that biotically it is through biofilm that we'll see PFAS and PFAS contaminants degraded. The issue today is analytical techniques and what are the daughter products. Very limited understanding of what are the daughter products. So I'm at a site in Bridgeport, Ohio. That's a former manufacturer. We have concentrations of chlorinated solvents, primarily TCE is the parent, with concentrations that exceeded 1 million parts micrograms per liter. In some locations, way over the saturated levels. They have 3 operating pump and treat systems, providing basically hydraulic control at this time. They've been operating for over 15 years and are classically asymptotic at this time. The purpose of this evaluation was to identify sustainable alternative to their current pump and treat systems by designing a biostimulation strategy that not only addresses the dissolved phase contaminants, but that residual source mass that's acting as a continuing source. I'm going to talk about a proof of concept evaluation and a pilot study. There's been a subsequent treatability study performed, started in 2018. None of these applications have been full scale. Our goal is to enhance the activity of indigenous dehalorespiring bacteria so that it can use the chlorinated solvents in an electron acceptor, expedite source mass solubilization, maximize performance while minimizing site impacts. There's no above ground equipment necessary in our process. And what we'll talk about is we're seeing decades of sustainability after a single injection with our additive. Contaminant concerns: trichloroethylene, baseline 55 to 550 milligrams per liter, 30% TCE's aqueous solubility. We got 15 foot of alluvial silty clay and gravelly sand overlying a fractured sandstone bedrock. It's estimated 10-foot thick interval. It's all trapped in the primary and secondary porosity of the shallow bedrock. Cis is very limited, less than 15. There's no vinyl chloride, so very little, if any, daughter products are being produced. Pump and treat system's been operating for 15 years. Regulatory people are concerned about shutting it off. The owner is concerned about continuing costs. ERD enhanced the biostimulation strategy. We started in 2020 with a pilot study using passive release socks. You see the woman there holding a sock. In each sock, there's about 2 pounds of additive. These were 10-foot screen wells that we utilized. So we used 2 socks per well. So about 4 pounds per additive. They replaced 5 to 7 times during the study. I'm getting a little ahead of myself here. They were applied 5 to 7 times. So in total, at the 3 monitoring wells where this pilot study was performed, about 25 pounds of additive in total was applied. In 2015, because of the positive results of the 2012 PRS study, they did a couple of injections using a 12% slurry, additive slurry, a little over 1,000 pounds of additive per 1,000 gallons of water each. They anticipated a 35-foot area of influence. And I made note that ERD enhanced goes in with the viscosity similar to 2% milk, and outside temperatures do not affect viscosity change. If it's 40 degrees outside or 80 degrees outside, the viscosity of the additive is maintained thin, enhancing distribution subsurfacely. One of the wells at the pilot study, I'm just going to go through a few of them because time is short. At MW30A, a baseline TCE was 30,000 micrograms per liter. You'll see at the bottom left, I have a period of amending. That was when they replaced socks every 6 to 8 weeks for about 5 or 6 events. And you will see initially we have a massive reduction in total CVOCs, starting at 39,000 parts in over 14 months. We had 99, 98, 96, handsome reductions in the total chlorinated volatile organic compounds present. Overall, after 4 years, in 2017, we've seen a 99.3% reduction. This is 4 years after 24 pounds of additive was deployed. We thought maybe it would last a year. Ethene was recorded throughout the evaluation, confirming we had complete transformation of the TCE. One thing I want to note is MW32 was the control well. But before I get there, the 2 other wells at MW31, where the same amount of additive was applied, we had a 99.98% reduction of TCE and basically a 90% reduction in total CVOCs. And if I made note, a pilot study using a sock is going to create a 1 to 2 meter area of influence. These areas are within a isopleth of 100,000 total CVOCs plus. So there's continuous advection coming into these minimal treatment zones. And this was only to determine, hey, is this going to work at this site? At MW38, the other augmented well, we saw definite, very handsome reductions and a 250% increase in ethene, again, confirming complete biotransformation. But I showed this graph here at MW32. That was the control well. And you can see by the blue lines, halfway through the process, nothing was changing. But in the middle, in February, January, February of this process, you'll see that all of a sudden, the ORP skyrocketed, and the contaminant levels decreased substantially. The client asked me, what's going on here? Why is it changing? We did not put additive in here. Well, what was happening is we classically in New England get January, February thaws. So we had a surface water intrusion into this monitoring well. And what I'm showing here is the importance of the parent-parent-daughter ratio when you look at a chlorinated site. You want to compare the molar changes, not just the dissolved phase concentrations. In the way I was able to demonstrate that this was dilution, not a dilution and not a solution for contamination, as you see that the precipitous drop in both the sulfates and the TCE levels, but the parent-daughter ratio doesn't change at all. That blue line that goes horizontally across the line there. That means there's absolutely no biotic activity ongoing during those reductions. What the tech had told me later was, yes, the well was completely submerged in surface water. He had to build a coffer around it, bail it out, then open the well before he could sample. Well, that well's integrity was shattered. That surface water had gone in and flushed everything out. And again, this is the classic solution to pollution is dilution example. During this process, we also had heterotrophic plate counts taken using biotraps, looking at DHC census. At the amended wells and the control well prior to the SOC deployments, we had minimal Dihalococoides species present. 2 years later, the amended wells all showed an increase in the DHC populations. The control wells showed none. And the biomarkers for complete biotransformation was recorded at all amended wells. None were recorded at the control well MW32. So based on these results, they went ahead and they did an injection study. But first, we realized sustainable reduction in ORP, enhanced electron scavenging, expedited residual mass solubilization performed by the microbes themselves, and complete biotransformation. So they went on in 2015, installed 2 bedrock wells, they anticipated a 35-foot area of influence. We had 130 milligrams per liter baseline TCE. We had a performance network of 8 down gradient wells to be monitored. Treatability was initiated in 2015. 24 months post the injections, we saw 99.9, 99.7, 99.5% reductions at monitoring wells 50 to 60 feet down gradient from the injection point, twice the distance they anticipated for the area of influence. And again, ethene was recorded at all down gradient locations. 24 months again, 2 years later at MW42, 50 feet down gradient, we saw a 99% decrease from 130 to 680 micrograms per liter. No, it's not compliant, but remember we have continuous advection of massive concentrations of residual mass up gradient into this treatment zone. DCE decreased 33%, and then slightly increased as respiration was occurring. Ethene range from 1.7 to 2.5, again showing that we had complete biotransformation. And the pH remained stable throughout the entire time, and VC was never detected. At all of our sites, we see ethene generation concurrent with cis degradation. We see very little vinyl chloride buildup or production, and we see no cis stall. And again, we have a site in Lebanon, New Hampshire here, where after 1 injection, I have 20 years of reducing conditions. So I just want to go back real quick. At the PRS study, we wanted to think about sustainability. It's been 8 years now since they put 24 pounds into these wells. And we're still seeing 99.9% decrease. There should be, for 8 years post in the 2012 deployment, 99.9% decrease basically at all the amended wells. And at the control well, which remained non-amended through 2017, concentration levels reached 1 million parts. They then did another injection. This was the 2018 injection, where in 2 years, we've seen a decrease in total CVOCs of 92%. There's still contaminant present, but what's important, we're seeing the parent-daughter ratio decreasing from basically 100%, all parent, to 16.7%, indicating solubilization of residual mass, destruction of parent contaminant through a biotic process that's sustainable. Microbial data again in 2017.
The time is running out, please.
I'm sorry, am I done? Okay. The same thing with the microbes happened. So our observations, meaning we saw continued increases in population densities. We create a centrophic behavior, or centrophic relationship between the dechlorinators and the fermenters and the methanogens. We increase and enhance biosurfactant production. We create a biofilm, which I'm not going to get a chance to talk about today, but we see the consistent realization of 99% reductions. In contrary to a lot of organic studies that says you're going to get 2 to 3 order of magnitude reductions, we're seeing 3 to 4 orders of magnitude reduction at all our sites, biotically. Let me get to here, hypothesis. I'm going to skip there. Conclusions. Prokaryotes are older, organized, and more experienced than eukaryotes. They're ubiquitous throughout the world. If we keep things anaerobic and enhance that ecosystem to allow those microbes to develop, they will adapt in very short time to the available energy, what we call a contaminant in their presence. In doing so, we maximize chlorinated and halogen or contaminants being used as electron acceptors and realize long-term destruction. There we go. I'm going to go right to there. I'm sorry for going too long, guys. It's a big site. It's still ongoing. I could share all of this with anybody. Just get in contact with me. Didn't do so hot this time, but hopefully next time I'll do better. Have a great day. Thank you so much.
Ken, thank you very much indeed. I'm going to hand over to Walter to introduce our next speaker, but if I could put a plea into the speakers to email me their slides ahead of the panel discussion, that may well help me ask more penetrating questions. Walter, over to you.
Thank you, Kent. Again, yesterday you were full of energy and today as well, apparently, so I'm happy to observe it. The next presentation is a French case study. I'm really pleased to also have some French cases on the controlled alkaline degradation of hexachlorocyclohexanes for the in situ remediation of a high velocity anisotropic aquifer from the lab to the field. So it's always interesting when we have field cases as well. So I'm really curious about the results of this study, and I give the floor to Mr. Bouzy.
Thank you. So hello everyone. Today I will talk about the results we got at lab scale for the controlled alkaline degradation of hexachlorocyclohexanes for the in situ remediation of a high velocity anisotropic aquifer. So this work I'm about to show is a part of the famous project that was co-founded by the French Environment and Energy Management Agency. It actually involves 5 industrial and academic partners in the domain of soil remediation, and it aims at developing and assessing new technologies for the remediation of anisotropic high velocity aquifers contaminated by chlorinated compounds. So the final goal of the project is field assessment of technologies on a study site. The study site is an active chemical plant. It's located above a highly anisotropic soil in which flows a high velocity and deep aquifer. So the water velocity is around 10 meters per day, and the aquiclude is located 80 meters below ground surface. So on this site, a contamination by hexachlorocyclohexanes, HCH, and 3-trichlorobenzenes, TCBs, was observed initially. So this contaminant is probably mostly absorbed since no known DNAPL is known. So in this case, in situ remediation is advised since the access to contaminant is hindered because of this high depth. However, when using traditional fluids like water, soil anisotropy leads to uncontrolled radius of influence, to fingering, to preferential flows, and the heterogeneous distribution of amendments. Thus, the permeability zones where the low permeability zones where contaminants are often trapped are badly swept and remain untreated. So these problems led to the use of viscous but shear thinning fluids less affected by these gravity and anisotropies, such as xanthan polymers to deliver alkalinity to these strong permeability contrasted aquifers. And also maintain their action by blocking the groundwater flow in the treated zone. Also in this study, we saw the degradation kinetics of the contaminants. So the first part of the study was to use two alkaline agents and to compare them. So we used sodium hydroxide and calcium hydroxide, both in xanthan solutions. So the first part, as I said, was to study the rheology of these solutions of xanthan solution in bulk in presence of sodium hydroxide and calcium hydroxide. The reference here was an alkalinity-free xanthan solution. So as we can see here, on the left of the screen, the overall rheological behavior of the three solutions can be described using the cross model. And as we can see also from these three curves, alkalinity has really a detrimental effect on the viscosity, on both the viscosity and the shear thinning behavior of these solutions, due probably to the perturbation of the associative behavior of the xanthan polymer. However, this perturbation of viscosity increases in presence of calcium hydroxide microparticles. Nevertheless, even though we have this detrimental effect, the fluid viscosity remains around 400 times higher than pure water. However, this detrimental effect of amendment on viscosity is much lower at high shear rates. Then after that, the porous medium rheograms were also obtained from the injection of calcium hydroxide suspensions in xanthan solutions. So these injections were carried out in columns using two soils from the field, having two different permeabilities at 9 and 850 darcies. So those results here show were obtained using these two equations we can see here at the bottom from the pressure gradient measured during the injection carried out in the soil column. What we can say is that the rheological, the behavior of the calcium hydroxide suspension in xanthan solution, both in bulk, as we can see here, and in soils, in the two soils, are very similar. And this demonstrates that the shear thinning behavior of the solution increased with the shear rates in these soils. So injections in field should be performed at the highest velocity, always being careful to avoid soil fracturing by not exceeding a certain pressure limit. After that, the alkalinity breakthrough curves were carried out in columns, in small columns filled with the fine sand from the field, as we can see here on the left of the screen. So the alkalinity of the recovered effluent was monitored by sulfuric acid titration, and in total we have injected around 9 porous volumes. So the plateaus of the relative alkalinity at the output of the column reached unit here, as we can see here, after less than 9 pores volume. Obviously, the plateau for the tracer here, sodium hydroxide, was reached more rapidly, because it has behaved as a conservative tracer. However, for calcium hydroxide microparticles, we have evaluated a retardation effect of around 1.2 compared to sodium hydroxide. And the alkalinity transmission was evaluated here at maximum at 91%, which demonstrates actually a fast and a high transmission of this alkalinity through a very low permeable soil, despite about half of calcium hydroxide microparticle was in solid form. So then what we did after the injection of calcium hydroxide, after these experiments, so the alkalinity was measured in each 2 centimeters of the column. So alkalinity accumulation was observed in the input of the column at around 10, in the first 10 centimeters of the column. So it decreased exponentially with the length to reach coarsely the values of the injected suspension. So this exponential behavior is explained by the balance equation on amendment injection through a filter medium, which is here the fine sand we used. However, in this case, the observed accumulation here, as we can see here, only resulted from the delayed transmission of alkalinity due to the size of calcium hydroxide microparticles. So in this slide, I will talk about the measurement in permeability contrasted sandboxes, and I will start by presenting the experimental setup we used. So this sandbox was filled underwater by with two media, fine sand and coarser sand, having permeabilities of 95 and 850 darcies. So here we can see that the colored water circulation simulating the groundwater flow was injected into the sandbox using a peristaltic pump at around 10 meters per day to mimic field conditions. So the reagent solutions here were injected through an opening at the back of the sandbox. So in this study, sodium hydroxide in water was used as a reference, then in xanthan solution. So the reference was sodium hydroxide in water compared to sodium hydroxide and calcium hydroxide in xanthan solutions. So as we can see here, the universal indicator was chosen to monitor pH changes of the injected alkaline fluids in the sandbox, since this indicator exhibits a purple color at pH 12. So the first step of this comparison was the injection of alkaline fluids in the most permeable material, as we can see here by the black cross in the middle of the sandbox. Actually, to see how far the treatment fluid could spread isotropically in the surrounding materials and also resist to groundwater flow. So as shown here in the top, the reference solution only propagated in the high permeable layer, in contrast to the solution in xanthan solution, which also penetrated the low permeability material, as we can see here. So sodium hydroxide the second case here, sodium hydroxide in xanthan solution better penetrated the low permeability layer, slightly better than calcium hydroxide, since due to its better rheological behavior, as we observed earlier. And so besides, in contrast to water or the reference here, no fingering was observed when the two xanthan solution were propagating into this sandbox, which means obviously a better controlled delivery. So after the injections were carried out, the simulated groundwater flow was colored in red to study the longevity of this injected fluid in the medium. So in absence of xanthan, we can see that only 0.68 porous volume were removed all of the injected solution. In contrast to the reference, the groundwater flow was effectively diverted in the low permeability medium when xanthan solution were injected in the high permeability medium, and for both cases here. So the injection of xanthan solution produced a markedly long-lasting blocking effect, which diverted groundwater flow out of the treated zone. And this effect was also observed for the monitoring pH value. As we can see here, no pH value changes were observed in the pH values. Then the persistence of the calcium hydroxide suspension in xanthan solution always injected in the middle layer, the high permeability material, was studied for around 18 days, which corresponding to more than 150 porous volume of groundwater. And at the last day, we decided to color the groundwater to see for a better visualization, to see what happened exactly. So as shown here, the erosion of the viscous xanthan solution was observed at around 10 days, which mainly arose in the high permeability layer, up and downstream. So after 18 days, the treated zone was eroded by around 20%. However, it remained strongly alkaline, as shown by the purple color. So these results suggest that the injection of reactive suspensions, such as calcium hydroxide, and their long-lasting activity and strongly permeable, contrasted, and high-velocity aquifers may be achieved. So the last part of the study is the alkaline degradation of HTH and TCBs in the contaminated fine sand from the field. So this study was carried out in columns once the calcium hydroxide in xanthan solution was injected. We observed
2 more minutes.
Okay, we observed a fast degradation of the HCH at pH 12 and production of 123 and 124 TCBs. So regarding the metabolites of HCH degradation, 124 and 124 TCB was the major product. So our results suggest a dehydrohalogenation of HCH to pentachlorocyclohexane followed by TCBs. So to conclude this study, so despite the fact that strong alkalinity and calcium hydroxide microparticles have harmful effect on the viscosity of xanthan gel, this property is actually maintained, and so is the shear thinning behavior. In contrast to water solution, the alkaline gel have shown lack of fingering and enhanced stripping during the propagation in the anisotropic to D sandbox. Breakthrough curves for alkaline xanthan solution carried out in silty sand demonstrated the fast and high transmission of alkalinity at low pressure, and injected xanthan gel demonstrated also a persistent blocking effect in the treated zone and groundwater flow diversion. Despite the high velocity groundwater flow, the long-lasting alkalinity in the treating zone matched the degradation of most HEH and their TCB metabolites. As a perspective, a monitored 3-scale pilot with alkaline injection between 8 and 15 meters depth and the contaminated ground layer was supposed to happen this year, but was delayed because of COVID-19 and is hopefully planned for next year. Thank you for your attention.
Thank you as well, Paul.
I was going to say thank you and hand over to Piotr to introduce our next, I think, final speaker of the session. Keep those questions coming through, folks.
Okay, thank you all. So let's see the next presentation, a case from Brazil, remediation of chlorinated solvent source area through excavation and in situ chemical oxidation. Please, Gert, up to you.
Hi, thank you, Piotr. Good afternoon or good evening, everyone. I'm working for Ramboll, an international consulting and remediation company with head office in Denmark, and I'm based in the Sao Paulo office in Brazil. So I will show you one of our case studies in the state of Sao Paulo, of the remediation of a chlorinated solvent source area in the unsaturated zone, using a combination of techniques, including excavation and ISCO. So I will talk you today in 15 minutes, and I promise I will stick to the 15 minutes. I will talk about a conceptual site model, specific challenges we had for source zone investigation and remediation in this case. What was our strategy for source zone remediation, and then I will talk in a bit more detail about removal of underground structures and excavation we did, and the application of ISCO in the unsaturated zone. And finally, I will show you some results and some lessons learned. So our site is located in the state of Sao Paulo in Brazil. It's a combined site with 2 separate industries, who used to operate as a car parts manufacturing facilities. For these car parts, they used PCE as a degrading agent, and they used they had an underground storage tank for PCE located in red, as you can see. You can also see on the diagram that we have a residential area located down gradient of both former industries. So an underground storage tank, PCE, that doesn't promise much, and indeed it did form quite some large-scale contamination. So on this figure, you can see the results of our site investigation, which took several years and had several steps, which included also high-resolution site characterization with MIHPT. And so we found out there is indeed dissolved plume of chlorinated carbons of PCE and the degradation byproducts, TCE, 1,2-DCE, and vinyl chloride, and which in total generated a plume of more than 200 meters, extending below not only both of the industries, but also below the residential area down gradient. In this area, the groundwater level is relatively deep, located at 14 meters depth. To complicate the matter a bit more. A bit more about our conceptual site model. You can again see the former underground storage tank of PCE in white below the most up gradient industry. This is, according to our conceptual site model, this is the main source of contamination. It's not the only source, but it's the principal source of contamination. Our aquifer is an unconfined sandy aquifer with some clay lenses in between. We have a hydraulic conductivity in the order of 10 to the minus 4 centimeters per second. Some emergency remedial measures have already been taken place to protect receptors. So we have a pump and treat system operating there, basically acting as a hydraulic barrier to contain the plume and stop it from continuing to migrate to the residential areas. And we also have a soil vapor extraction system, an SVE system in place with inclined SVE wells below some homes to mitigate vapor intrusion into these homes. So a complex site, complex problems, and I'm going to focus the rest of this presentation a bit more on the rectangle I'm showing in white. So basically on the source area of located in the unsaturated zone below the former underground storage tank. So we have some specific challenges here, not only for source zone remediation, but even for source zone investigation. Obviously, we know that we can only be effective in remediating our dissolved phase plume in the unsaturated zone if at the same time we can remove our source zone in the unsaturated zone. Unfortunately, we had very little information about the source zone in the unsaturated zone. Access limitations were the biggest challenge for this particular project, because the building in gray you can see on the figure still exists. To make matters worse, the former storage tank is actually located in quite a small room with difficult access within this building. So we couldn't even get a drilling rig in this room where the storage tank was located. So we couldn't even collect soil samples to better determine how big and what extent exactly this source zone in the unsaturated zone had. And we had, as I said, 14 meters of impacted unsaturated zone below the building, and we already knew that excavation of 14 meters would be practically impossible. So we did a lot of brainstorming. It all seemed quite difficult at first, and finally we came up with the following remedial strategy, which consists of 6 different steps. So first step was the removal of these underground structures. So within this containment basin of the tank, remove all of the structures. I will show you a bit more about that in the following slides. Then we did do some excavation, but it had to be manual excavation. So the maximum excavation we could manage within safety constraints was down to 5 meters below ground surface. As a next step, we did in situ chemical oxidation, ISCO, of the contaminated soil below our excavated pit using a solution of sodium persulfate. Next step was simply backfilling the excavation pit and doing compaction. The next stage was installing some SVE extraction wells around the former pit for extraction of residual mass in the unsaturated zone. So we installed these wells down to 10 meters below ground surface, and we integrated them to our existing SVE system. And then the next stage, and that's where we are at the moment, we are starting to implement this stage, is injection of nanobubbles of ozone and persulfate. That's an innovative ISCO technique we are using both in the unsaturated and the saturated zone to finally resolve the former source area and at the same time already tackle the center of mass of the plume in the saturated zone. So in the following slides, I will show you a bit more about some of the steps we went through. So here you can see some pictures of the underground tank basin before we started. So a lot of heavy structures still present there. So we managed to remove the concrete base and the bottom of our pit. This was already very challenging because obviously we have a confined space here. We had high vapors of PCE in this area, so an extensive health and safety system had to be implemented. We actually had to remove some of the side walls of one of the buildings to improve circulation and to facilitate access. When we broke down the floor, there was a metal floor. We actually discovered there were 2 metal floors within this containment basin, and between these 2 metal floors, we had pure product still standing. So we drained 1,200 liters of product between these 2 floors, and when we sent it to the lab, it turned out to be almost pure PCE. So at least this was already important to remove this secondary source of PCE, which even after decades of this tank operating was still standing there, and obviously which kept feeding our saturated plume. In the next step, we did some excavation, as I said, manual excavation. So this was very challenging because of geotechnical concerns and health and safety concerns of our subcontractors. In this pit, doing manual excavation, we only managed to get down to 5 meters. At the end of the excavation, we collected some soil samples, which are all the green dots you can see on the screen. 8 samples at the bottom of the pit, 8 samples at the side of the pit. And when we got the results back from the samples from the bottom of the pit, we saw still very high concentrations of PCE remaining there, in the order of 3,600 milligrams per kilograms of PCE. And then, of course, we were only at 5 meters depth, and our water table is all the way down to 40 meters depth. So we knew there was still a lot of residual PCE mass in the unsaturated zone to deal with. The next step then was an ISCO application in the unsaturated zone. So we used a mixture of sodium persulfate activated by chelated ion. We estimated that the soil oxygen demand, SOD, as the sum of the natural oxygen demand, which we determined in samples from relatively clean soil in the same area, and the stoichiometric demand of these high concentrations of PCE in the bottom of the pit. So we got to a total of almost 11 grams per kilogram of SOD. Before we did the application, we did some falling head infiltration tests at the bottom of the pit to estimate the infiltration rate. And then we did the application of ISCO simply by gravity injection of a total of 64 cubic meters of oxidant solution, which went down in about 8 cubic meters per day. We did that in 2 separate infiltration events, separated by a 3 weeks interval to maximize the oxidation potential. And we also alternated within each infiltration event batches of persulfate, where we applied a total of 4,500 kilograms, and chelated ion, where we applied 200 kilograms. We alternated them to, of course, have the reaction happening in the formation and not in our mixing vessel. Some results then. One of our main concerns during this application was not to apply too much volume of application, and so we were concerned about a surge in groundwater levels at 40 meters depth, which could cause spreading of the plume. But we monitored our monitoring wells around the area, and we didn't see any increase in groundwater levels, so we didn't cause spreading of the plume. After the ISCO application, we collected soil samples again in the bottom and the sides of the pit, and we saw reductions in PCE concentrations of more than 95%. So this demonstrated that the ISCO process was effective. And as I said, the next step is an ISCO application in the unsaturated zone and the saturated zone with nanobubbles of ozone and persulfate. So this is an innovative technique we've used in several other projects with Ramble in Sao Paulo. So instead of the classical approach of generating micro bubbles of ozone, we create nanobubbles, which are much more persistent, don't collapse so easily. They can much more easily disperse and diffuse within the grains of the formation to get to the contamination. And we've seen dissolved oxygen concentration reaching up to 20 milligrams per liter, so supersaturation of oxygen concentration because of this application of nanobubbles. So yeah, we have high hopes of this application finally being able to treat both the remaining unsaturated zone and the saturated zone. So finally, some lessons learned in this case. Well, ideally, you first complete your investigation, do 3D delineation of your source zone and your plume, and only then you do remediation. In this case, because of access limitations, we had to run both in parallel. So we first had to do the excavation to only then be able to get access to collect soil samples and then update the next remediation plan based on these intermediate results. Initially, we thought excavation was really not possible. We managed to make it work. We focused on inventive solutions. Health and safety was of paramount importance here. We put a lot of effort and time in our health and safety measures, and also our subcontractors were essential in getting this job done. All of the work I showed here was done over the last 6 months during the COVID-19 pandemic, which was particularly intense and still is in the Sao Paulo area. We managed to make it work through clear procedures of health and safety, strong communication with the client and with subcontractors. And finally, and I think this is a conclusion not only for my talk, but I saw that in several of the previous talks of today's sessions appearing, one single remediation technique does not solve complex problems. If you have contamination in different compartments, complex problems, you need really a combination of remediation techniques to do the job, and this is what we did here. Thank you very much. I also want to thank my colleagues who worked on this project and this presentation with me, Juliana Curi, Gabriel Garcia, Andres Cervelina, and Gustavo de Mello. I want to thank colleagues Felipe Campello, Arlindo Matos, my US colleague Mark Mejac, and subcontractors Paroxychem and Janssen Engineering Construção. Thank you very much.
Thank you very much, Gerd, for this interesting presentation. And still one presentation to go. Wouter, could you please introduce?
I don't have the presentation in front of me. I only see that the title is Disease Stall, Causes and Cures, and that Robert Borden will present it. So Robert, the floor is yours. We don't hear you yet.
Robert, just unmute yourself, please. We can see your slides. You just need to unmute. Perfect.
Is that any better?
This is better. Yes, indeed.
Thank you so much. Hi, my name's Robert Borden, obviously, and what I'm going to be talking today is about DCE stall causes and cures. I'm a professor at North Carolina State University and also work with a remediation firm, ES Remediation. What I'm going to talk about today is anaerobic bioremediation with emulsified vegetable oil. We've been doing this process for about 20 years. Literally, we've done it at thousands of sites, tens of millions of kilograms of material. And it's really a really straightforward process. You take the EVO, well, in this example, we use Pro, we dilute it with water, we inject. We've learned over the years that it's very important to inject additional chase water to spread that oil out through that formation. I'm going to really emphasize later on how important it is to get good contact and good distribution. We also like to flush any residual substrate out of the injection well. What we find is that if you leave a lot of substrate in the injection well, it can clog over time, and you can clean out the clog, but it's a bunch of work, and it's really much preferable. Versus if you inject water afterwards, we could clean out that well, and that problem gets minimized essentially. So anyway, once the oil droplets flow out from the well, they'll eventually stick to the sediment surfaces. Over a month or a while, the oil will slowly ferment, releasing hydrogen acetate. That hydrogen and acetate drives reductive dechlorination. Many sites we bioaugment, typically we find the substrate lasts anywhere from 3 to 5 years, some sites longer, some sites shorter. So it's a relatively low maintenance technology, and it's really pretty effective. What we have seen though is at a few sites, not the majority, but you know, this does happen, that we'll get, well, what might look like DCE stall. What I've got shown up on the screen is the dechlorination pathway for PCE, and I'm sure you're all familiar with it. If dechlorating organisms take what just happened.
We seem to have lost your screen, Rob. We can still hear you. You can just try resharing your screen.
Stop video, chat.
Press the green
share screen, the green on the bottom.
Ah, okay. Oh. All right. Okay, I'm back. Sorry about that.
That's it. Perfect. Thank you.
So PCE will dechlorinate. Essentially, there are microbes present that can strip off a chlorine, replace it with a hydrogen, and you proceed through this process, making TCE, DC. We tend to think that is continuous, but over time, we've come to realize that there's almost 2 parallel processes going on. The first process, where PCE is converted to DCE, at many sites really happens very, very rapidly. There's a number of different organisms that can carry out this process. These organisms tend to be a little less fastidious. They grow rapidly. They can use both hydrogen and acetate. They can fix nitrogen and produce their own ammonia. They can produce B12, and they tend to be a little less pH sensitive. So I'm going to show you some data in a moment that we're getting from PCE to, you know, essentially 100% conversion of DCE. I don't want to say it's easy, but it's pretty straightforward. Getting additional conversion of DCE to ethene and truly cleaning up the site. At many sites we see it's not that that conversion stops, but this second process is slower than the first. And so it takes more time and ends up costing more money. Why? Well, it turns out, I think most of you know, there's really only one well-defined organism that can convert DCE to ethene, Dolichocoides macardii. It grows, just the simple kinetics of the organism, it grows fairly slowly. It cannot use hydrogen or acetate. It needs hydrogen as electron donor. It needs an external source of ammonia. It requires an external source of B12, and it's much more pH sensitive. So there's a lot of different factors there that just pile up to make it, you know, this second step slower and just a little more complicated. So here's some example. What I want to illustrate for you is sort of approach we might use. This is a site, it actually was a research site we worked on for the ESTCP, the US Department of Defense Research Program. EOS Pro was injected at the site in 2006 and then again in 2012. You can see from 2006 to 2009, really outstanding PCE removal. Some of you may not, you know, readily convert, but 10 micromolar, that's basically, well, we're up here almost at 100 that would be like 10,000 micrograms per liter. 99.99% reduction of PCE and TCE going down here to essentially analytical detection limits in 2 or 3 years. So great results. Bad news is that while TCE went down, cis DCE, well, either stayed constant or actually even went up a little bit. We then made vinyl chloride began to increase. But at all that same time, that black line, we're making 10 micromolar of ethene. That would be 100, 200, 300 micrograms per liter. So if any of you do bioremediation, 200-300 micrograms per liter of ethene, that's really good. So we're making a lot of ethene, we're getting degradation, but we don't seem to be making any much more progress after about 2009. One of the ways we like, or I like to evaluate this is, I'll calculate this number called the sum of organic chlorine. And essentially all sum of organic chlorine is the molar concentration of organic ethene. In this case, it would be 4 times the molar concentration of PCE plus 3 times DCE plus 2 times DCE and vinyl chloride. And you can see here that same pattern, rapid decrease, about a log unit of in chlorine, but then we seem to sort of stall here. Well, I don't have time to share with you all this was the work, but we went back, we did some more looking, and what we found is that there was essentially an up gradient source of this zone that had continually releasing a small amount of TCE. We found that source, we later treated it. But the other thing is that there were some problems, or not problems, even though there was continuing source coming in, we weren't degrading the DC and the vinyl chloride quite as rapidly as we wanted. So we looked at ways to accelerate that. One of the primary ways was raising the pH, and I'll talk about that in a little minute. But eventually those measures took effect, and we were able to get both DCE and vinyl chloride very low, and essentially, what is that, over several log units of organic chlorine removal. Okay, so I mentioned this project. We looked at several sites, and essentially our conclusion of the project was that, as I said, PCE, TCE conversion to DCE at most sites is really quite fast. The logistical problem is that DCE conversion of vinyl chloride and ethene is just slower, and it's slower for a number of reasons. This is not DCE stall by the classic sense. We're making ethene. It's just simply the kinetics, or TCE degrades faster than the DC does. So our focus is on figuring out a way to accelerate DCE conversion, since that's the rate limiting step. That leads shorter cleanup times, and again, save money. Well, the net conclusions of that, sorry about that, people. My phone started ringing. Okay.
Robert, is that you with the noise pollution, or somebody else?
That was me. My phone started.
That's actually fine. I was trying to see whose speaker was unmuted and couldn't.
Sorry about that. So anyway, what we've identified is the sort of really key things is, step one, if there's still significant amounts of PCE and TCE present, you're probably not going to be able to accelerate further conversion of DCE. Just simply, the bugs like TCE much more than DCE, and until you burn up essentially all the TCE, you're going to be stuck there. Another issue, we see some sites low DHC numbers. As I'll show in a second, the solution to that, bioaugment. It's not that hard. We typically add B12 and nutrients at virtually all sites, just to make sure that that's not limiting. But actually what ends up being a more critical issue is, as I indicated, conversion of DCE requires hydrogen. Well, as I'll explain in a moment, distributing the hydrogen is challenging, and it really means you have to get better, more uniform oil distribution. You have to bring that hydrogen into direct contact with the TCE. And at many sites, we also see we have low pH inhibition, and I'll talk about that. Okay, so bioaugmentation, it's pretty simple. There's specialized cultures available. As I indicated, we do this at really most sites. There's an argument, you know, we don't want to add foreign organisms. It's expensive. The reality is it's not that expensive. It does cost some, and there is some labor, but, our experience is that if we can even save, 3 months, that will often cover the cost of bioaugmentation. Waiting costs money. There's monitoring costs, there's regulatory things, there's mobilization. It, in many cases, is just better go ahead, bioaugment, and make sure we get this process done quickly. Second issue specifically about vegetable oil, but we really find this is also true for lots of substrates, soluble substrates and other things. But specifically for vegetable oil or soybean oil, you see that picture in the upper right-hand corner. That's a model of a soybean oil molecule or a triglyceride. Soybean oil is got a glycerol in the center. That's really the cluster of red dots. Those are oxygens attached to 3 long-chain fatty acids. Before bacteria can use soybean oil, what they have to do is they hydrolyze the linkage between the long-chain fatty acid and the glycerol. And so they release glycerol and the long-chain fatty acid. Glycerol, very soluble, very easily biodegrade. That gives you a quick initial burst of hydrogen that starts the process. But I indicated these oils, they could last 3-5 years. Well, why? Well, the reason is that what happens is the oil sticks to the soil and then gets slowly degraded by this process called beta oxidation. A representative long-chain fatty acid in soybean oil is linoleic acid. It's got the formula C18H32O2. Well, the way bacteria chew on this is essentially they take that C18 carbon, they add water to it, and then they cleave it and they release a C16 and 1 C2. That C2 is acetic acid and a hydrogen. They can then take that C16, cleave it, release another acetate and a hydrogen. And they keep proceeding that process. They slowly whittle it down. And over time, they release, well, a lot of acetic acid and a lot of hydrogen. One of the advantages of oils is they actually release more hydrogen per mole than most other materials because they're more reduced. Well, okay, now let's talk about the difference between hydrogen and acetate. These long-chain fatty acids, linoleic acid, if you neutralize them with sodium hydroxide, you basically get soap. That's what your grandmother or your great-grandmother used to make. You take fats, you hydrolyze them with sodium hydroxide, you get soap. If it's a sodium salt, it's relatively soluble and move around. But if there's a lot of calcium or magnesium or iron, you precipitate material as soap scum. That material, that soap scum, is essentially immobile, which is sort of good and sort of bad. It's good in that since it's immobile, it's relatively low bioavailability. It lasts a long time. That's actually why when we inject oil, it'll last 3 or 4 or 5 years or more. So that's a good side. The bad side is since it's immobile, you really only produce that acetate and hydrogen where the oil is present. It doesn't. Now the acetate itself is relatively difficult to degrade. It doesn't have a high energy yield. Since it's not that good of a carbon source, it will migrate to some distance down gradient. As it migrates down gradient, if it interacts with PCE or TCE, it will degrade that. It's a very good carbon source for that initial degradation step. The challenge is hydrogen is very labile. It'll degrade very, very rapidly, both using an electron acceptor for the chlorinated VOCs we're trying to degrade, but it can also be used in electron acceptor or electron donor, sorry, for iron, for sulfate, for carbon dioxide reduction. The net result is hydrogen does not migrate any significant distance. It's really only present in fairly close proximity to where it was originally produced. And you can produce hydrogen from oil or propionic acid, butyric acid, valeric acid, many of the short chain fatty acids. However, you cannot produce hydrogen from acetate. So if you're in a zone where you only have acetate, you can get good PC, TC, and D degradation, but you will not get conversion of DC to ethene. You need to bring that hydrogen into direct contact with the contaminant and the bugs. Okay, how does this migrate? Here I've got results from 2 wells. The upper figure is actually a well where we actually injected EOS Pro into, and then we chased it with a lot of water. We spread the material out, but this well is surrounded by a zone of oil-treated soil. And you can see there shortly after injection, all the fatty acids increase rapidly. We're making acetic acid, but we're also making a fair amount of propionic and butyric acid and other longer chain fatty acids. So in this well, we have very good fatty acid distribution, great conditions for hydrogen production, which means great conditions for conversion of TC all the way to ethene. 10 feet down gradient, you see, well, we did get an initial burst of fatty acids shortly after injection, but really the large majority of that was acetate. And then after 6 months, pretty much all that went away, and really the only thing left was acetate. And this is really common. So we've got a zone down here. Now, if we have PCE or TCE or higher chlorinated compounds in this region, we'll get good removal of those. But since there's very little long chain fatty acids here, we won't get hydrogen, and you're probably not going to get good DCE removal. The take-home message, you need to bring the oil into close contact with a contaminant. You can't hope for spreading. You need to bring the substrate to the pollutant. Okay, another point here, pH. In that early slide I showed you, we would add a hydrogen and it would bump off H plus and a Cl minus. Well, that's hydrochloric acid. So as we're going through this process, you're dechlorinating, you're releasing hydrochloric acid, and you can lower the pH. If you look here for TCE conversion to DCE in a bioaugmentation culture, yeah, the optimum degradation occurred at pH 7, but you can see here at pH 6.5 and actually all the way down to 5.5, really pretty good conversion. This process is not terribly sensitive. However, when we look at vinyl chloride degradation, you see here, again, pH 7, essentially, very rapid conversion of vinyl chloride to ethene. pH 6.5, a little slower. pH 6, a lot slower. And pH 5.5, really completely inhibited. So the Halichocoides McCartyi is much, much more sensitive to pH changes. And if you want to get good removal, you need to raise the pH. Well, you need to raise or keep the pH neutral. Okay. So lessons learned. ERD works. Like I said, we've done this at thousands of sites. We know what's required to get good conversion of DC to vinyl chloride to ethene. I've gone to those things. The key is, you know, engineering your site to do that. I did not have enough time, and I know it's happy hours coming up in a moment, so I don't want to take too long. I am doing a short course on Friday where I won't just sort of tell you you need to do this, but hopefully we can show you how to bring the oil into direct contact with the contaminants and how to buffer pH. So I hope you'll join me then. And I think my last slide here is, I've been working for a long time on this website called EnviroWiki. I'm going to put my sales pitch in there. I hope you go check it out. It's got a lot of very, very good information on different groundwater remediation technologies, anaerobic bioremediation. You can see a bunch of articles here, and design tools, different contaminants, ISCO, ISCR, lots of different things, and I hope you'll check it out. And that's all I have.
Robert, thank you so much. And maybe you can put the URL for EnviroWiki into the chat box.
The URL is www.enviro.wiki.
Excellent. So time for questions. I'm going to run over the hour for a little bit. Piotr, I think you've got a question from Marcello Carboni from Regenesis, who kicked us off a couple of hours ago now.
Indeed, it was a very nice presentation, actually a very practical one, because I understood that the site was still working while you were doing different decontamination treatment. I just wanted to know the pilot phase. You were talking about pilot tests. How long did it take to design them, to establish and to have some sound results, then to start the real remediation? It was a couple of days, it was several weeks to be sure that the method is working?
If we are talking about the design phase, so a preliminary approach and design the pilot could take, let's say, 1 to 2 weeks, but then needs a lot of refinement and discussion, especially between us and the consultant, to see if all the input parameters are correct, etc. And in some cases, this was not the case, but in some cases, some secondary parameters are missing. So could be better to then just get some new samples for groundwater and then get these secondary parameters. Otherwise, we could risk maybe to overdose sometime. The injection phase was very quick. So, I mean, the pilot was with injection wells. So they needed to inject, to drill the wells down. So it was about, I think, 6 injection wells plus some new monitoring wells installed. But apart from that, the injection phase on site was about 3 to 4 days. So it was very, very quick. Then it was decided since the beginning that the monitoring phase would be 6 months, and it was quite a pity because then the budget for the monitoring phase for the pilot just stopped. So the 6 months I showed you were just what was available. So we are missing all the data from 2016 to 2018 when they start monitor again for the full scale. But 6 months, I think for this kind of technology is quite a good time frame for monitoring.
Marcello, thank you very much. George, I've got a question for you from Daniela Innocenti. The question is basically, when you're designing your injections, do you need to take into account the characteristics of the microbial community to avoid a possible overdose, which then either slows down or stops biological degradation?
It's a great question because the application use of a lot of different surfactants can actually have a very inhibiting effect on a lot of different types of bacteria, aerobic, anaerobic, and facultative. The bacteria that we use are actually biodegradable to 3 international standards. And at the concentrations that we apply, if our clients apply it at their recommended dosages, we actually don't experience inhibitory effects in the bacteria. In fact, by making the contaminants more miscible in solution without forming a micelle, we actually observe that the bacteria actually take off, and that whole mineralization probic, aerobic, anaerobic, or facultative processes with petroleum hydrocarbons or even chlorinated solvents, by example, chugs along quite well and more efficiently. But we're not a bacteria and we're not those additives. So again, in some cases, we're just facilitating that. But yeah, not too much of an issue.
George, thank you very much indeed. Question for Kent, and we're sticking on the microbiology side of things. Kent, you mentioned that no vinyl chloride was detected throughout the study you were talking about. What's the reason behind that, given that normally vinyl chloride is detected at some point on most sites because it's a part of the dechlorination series of breakdown?
Quick clarification, it will be detected at very low levels, but it's consistently detected with ethene generation concurrent with cis degradation. The reason we find this and believe this to be true is our carbohydrate converts to glucose, which is a gold standard for microbial energy, faster than others on the market. In doing so, we create, I got my notes here, we have the CO2 then, we create massive amounts of CO2, which creates acid. As the system becomes anaerobic and all the other alternative electron acceptors are scavenged, the residual carbohydrate undergoes fermentation and supplements more formation of molecular hydrogen. We furthermore create a biofilm, an enhanced biofilm. And with it, so that within this enhanced biofilm, we're creating an in situ bioreactor, if you will. And you just get maximum efficiency with complete biotransformation by the microorganisms operating. And just one further note, within that biofilm, they don't care what the pH is in the bulk water. Historically, most tests, most evaluations are looking at planktonic bacteria swimming about in samples in a laboratory, not necessarily adhering and allowing to be formed into a biofilm. We're not looking at the sessile bacteria. It's the sessile bacteria is where they become smart and where they become to adapt and they maximize their efficiencies. In Ohio, we have complete biotransformation in months, 100% degradation in months at a 3.86 pH in the bulk water. In Saudi Arabia, similar with dichloroethanes with a greater than 10 pH in the bulk water. Within the biofilm, they don't care, they're protected. You gotta form that biofilm.
Great, thank you very much indeed. Walter, I think you've got a question for Iheb, is that right?
No.
Oh, okay.
The question is that we have to be careful, and that's a remark of Marco, that we have to be careful with the closing, as it's an abrupt closing at 7:50.
Marco and I have been negotiating. We have a bit more time. Iheb, I'll come back to you in a second. Piotr, I think you've got a question for Gert, is that right?
Yes, indeed. So it was also a big exercise that you did also in difficult times currently. So my question would be twofold. So there is some, let's say, chemical treatment and excavation. And I'm just wondering, was there any economic study done how much it costs in total? Because a lot of important devices were used. And does COVID experience make the price higher significantly or not?
Okay. I can't really give you any numbers here. I think all the work we did definitely paid off because remember we have a 200 meters long plume and already a lot of effort had been put in the past in emergency remedial measures in tackling this dissolved plume. But we knew that as long as we don't tackle this unsaturated zone source zone, we would just be keep remediating with the source continuously feeding. So I think what we spent on this source zone remediation was relatively low in comparison on the rest we have spent and we will still be spending on remediating the saturated plume. So it was definitely worth it within the overall project timeline. Did COVID make it more expensive? Not really, not really. We had a bit more expense on additional vehicles. For instance, we didn't allow people to use a vehicle together, so people had to come in separate vehicles, things like that. But no, well, we spent some additional time in health and safety preparation, etc., but nothing really significant.
Good, thank you very much indeed. Robert, a question for you. What THC population do you consider to be low and therefore requiring bioaugmentation? And as a percentage, just how much more expensive is bioaugmentation rather than biostimulation? So when do you do it and what's the cost premium, I guess?
Additional costs, probably 5% maybe of the total project cost, maybe. Well, I'm going to actually say 5% of the remediation cost. And if you consider all the site characterization and other work that goes in it, you know, maybe only 1 or 2% of the total project cost. So it's really not that expensive in the long term. And as I said, we feel pretty strongly it's beneficial at many sites. In terms of DHC counts, there's really sort of two sides of it. It's before you start the project, if we had DHC counts and actually also vinyl chloride reductase counts of 10 to 100 per mil, we would actually think that was pretty good as an initial starting point. If we're successful, and we are most of the time, and we've got good pH, good nutrient levels, those initial counts will jump up to 10 to the 4th, 10 to the 5th cells per mil. So, you know, at least 1, 2, hopefully even 3 order of magnitude increases. And that shows that, well, we have really good conditions for the bugs. We're not, now for design purposes, if the bug counts initially are below 100 cells per mil, we would probably bioaugment, and we bioaugment at a dose that's probably closer to 10 to the 4th to 10 to the 5th, just because, well, like I said, these organisms grow slowly. If we can add some more to start with, if we can jumpstart the process, then, you know, time is money, and it's just cheaper to get the process along. One thing I will say is I've heard, you know, this discussion about where the pH and whatever, but you really need to think about what the environment the bugs are living in. If the pH of the aquifer is 6, and you're really effectively degrading the pollutant, those pollutants are bringing in PCE and DCE, and they're exhaling hydrochloric acid. So they're bathed in a pool of hydrochloric acid. If they're, you know, if they're doing their job, if they're crunching along, if they're burning up contaminant, they're making acid. And so the local pH right in the vicinity of the rapid dechlorinators, you have to expect is going to be lower than the background pH, which means, you know, we need to keep it up more neutral, and well, that's our position.
Thank you very much indeed. And don't forget, Robert, short course on Friday afternoon. Piotr, if you don't have a question for Ehab, I've got one. He's smiling but muted, so
I was muted. Yeah. So please go with your question.
Ehab, thank you very much indeed for your presentation. I liked the use of the small models. I'm interested in the FAMOUS project. Can you tell us a little bit more about the scope of that project and how your work fitted into it?
So, like I said, the project basically involves 5 partners, industrial partners and academic partners. So our part in this project, so we are the one of the academic partner as the University of Bourgogne-Franche-Comté in France. So our main job was to assess in lab scale different strategies and technologies using and trying to be as close to field conditions as possible using these small models to try to prevent any problems that can happen or in field after. So our job was to test all the possible situations and be in the, let's say, the most difficult situations to be sure that when we are going to apply what we developed in lab scale into the field, everything will be fine. So even though the scale is not the same, but we try to use the field materials to keep the field geology and everything. So hopefully what we developed at the lab scale will work when we test it in field next year.
Great, thank you very much indeed. I'm going to close the session there by thanking all the speakers. Most of them have explicitly said, get in touch with them if you want a copy of their slides. I'd also like to thank my co-chairs, Wouter and Piotr, and Marco for organizing all this. And thank you for staying with us for the entirety of the session. I'd encourage you to engage with the RemTech chat. You have to bring your own coffee, I'm afraid, or indeed your own Italian red wine. But do continue to engage and have that conversation, because that's what makes the conferences come to life. We've got the program tomorrow morning, virtual demos, and then emerging pollutants, the circular economy. And you couldn't have a remediation conference without PFAS these days. So that's the 23rd of September. Enjoy your evening. And I'm very sorry we can't chink wine glasses together, but let's do that metaphorically. Have a good evening and good night.
Thank you. Thank you.
Bye-bye. Thank you.
Thank you, Wouter and Paul and all speakers.
Thanks, everyone.
Thank you.
See you tomorrow at 9 o'clock. Don't miss the virtual live demo.
Marco, thank you. I'm going to sign off and run to the gym.
Okay, do it, because yeah, I know. While I go to the table to eat.
Okay. I'll see you later.
See you later. See you tomorrow and next days.
I'll go to the gym as well.
You too.
Bye.
Well, you don't need.
It's preventive.
In general, to the gym goes people that doesn't need and people that never get slim. So yeah, that's the what I found in the outside the gym.
It's also for fun, because people are speaking over there, so I can not really do exercises, but I can speak with them.
Okay, so yeah.
Italy, everybody speaks here.
Yeah. Okay.
Ciao, everybody. Yeah? Bye.
Bye, Piotr.
Bye.
Bye, Gerd.